Our quadratic function then, the most basic quadratic function of them all, y equals x squared. Together with the linear function, they are the building blocks of every polynomial, because every polynomial can be factorised down to be a combination of quadratic and linear factors. Every quadratic, just like the straight line we saw, can be transformed from y equals x squared via translations, rotations, reflections, dilations, but we can get every single possible one from y equals x squared. So how do we recognise the quadratic? There's our general form, y equals ax squared plus bx plus c, but this time we're looking for the highest power. Highest power of y, in this case is 1, the highest power of x is 2, we have a quadratic. So some ideas that can assist us with quadratics. That completing the square idea can be very useful. If I factorise that quadratic down via completing the square, again by just looking at the equation, I can see the vertex straight away. There it is. The vertex for that would be hk. So once I've factorised it, there it is. A, of course, measures the concavity of the shape. So back to the example that we did yesterday, I'm not going to sketch it again, but sketch the parabola x squared plus 8x plus 12. If I complete the square on that, well, half the coefficient of x is 4, so I know it's going to be x plus 4 squared. If I was to expand that out, I'd get 16, not 12, so I need to subtract 4. I can see the vertex straight away. There it is, it's minus 4, minus 4. The x-intercepts, well, now that I've completed the square on it, I can just go x plus 4 squared is 4 and find them that way. Minus 6, minus 2. The question we saw yesterday about this, write down the quadratic with roots 2 and 8 and the vertex is 5, 3. Well, if the vertex is 5, 3, then it must be in this sort of form. Substitute the point that we know and we can work out, oh, k is minus a third. So there it is in the completing the square form. If I was to expand all that out, I would end up like so. Which was the same answer we got yesterday. The discriminant, here's another way I can find it using just the discriminant. Remember, b squared minus 4ac, that bit under the square root sign is what we call the discriminant because it discriminates between the roots of your quadratic. And there's your vertex. We know the x value is minus b on 2a. The y value is minus the discriminant on 4a. The solutions therefore become minus b plus or minus the square root of the discriminant, because that's how we said the discriminant is formed. It's the bit under the square root sign. This has some implications though. If the discriminant is less than 0, then we know my picture is not going to have any x-intercepts because we'd be saying the square root of a negative number, which of course doesn't exist, no, not with real numbers. So we can't have any x-intercepts. If it turns out that that discriminant is 0, then it must just be one x-intercept. Now, is it right to call it an x-intercept if it's just touching? So it's the x-axis is a tangent because we're going plus or minus 0. And if it's a positive number, then we know, oh yeah, we are going to get 2 x-intercepts. Same example again. Sketch that parabola. How would I use this idea? The discriminant I can work out. It's 16. Therefore my vertex is minus b on 2a, so minus 8 on 2, minus the discriminant on 4a, so minus 16 on 4, negative 4, negative 4. Where it becomes really, really useful, that idea, is if the question is something like this. Find the maximum value of this quadratic. Now I don't have to worry about finding now the axis of symmetry and then substituting in to get the y value. I can just go, okay, I know the maximum value will be minus the discriminant on 4a. And I can get it without having to worry about finding the x value that it happens. Now let's talk a bit more about this thing, the discriminant. It's basically telling us things about the roots. Are they rational? Are they irrational? It's discriminating between those things. As I said, if the discriminant is greater than 0, cuts the x-axis twice. Yes, it has 2 x-intercepts. As far as what the roots actually are, we know they exist. They're real. So there's 2, and they will be different. So there'll be 2 different real roots. Whereas if it's equal to 0, you still have 2 roots. They just happen to be the same. You've got a double root. It only touches the x-axis once, and if it's less than 0, you don't have any real roots. You still have 2 roots, mind you. Now the 2 roots are imaginary roots. Every quadratic will have 2 roots. but this one will never touch the x-axis. If that discriminant turns out to be a perfect square, then we know the roots must be rational because we can find the square root of it. So I'll get plus or minus and it'll end up being a rational number rather than an irrational number. So we're going to describe the roots of this equation. Well, the discriminant is 60 and that's a positive number. So what are all the things I can tell from that? I know they're going to be different, I know they're going to be real, but I also know they're going to be irrational because I can't find the square root of 60. So I've got two different real irrational roots. This time they're saying, well, if this quadratic has no real roots at all, what's the value of k? Well, what was my condition? Unreal, or no real roots occur when the discriminant is less than 0. b squared minus 4ac has to be negative. We solve that little inequation and we get k is greater than 2. So as long as k is greater than 2, we'll end up with a quadratic with no real roots. Okay, that shall do us for today.